And we're back for part 2. Hope you're refreshed. Again, notebook out. You're going to be doing some math with me. You're also going to be doing a lot more of detail-orientated conceptual stuff. Let's talk about Newton's second law of motion. This law is all about happens when you're not in equilibrium, which means that there is an unbalanced force or forces at work on the object. Let's call this amount of unbalance the net force, which I can show through two different symbols. Sigma F or F net, your choice. And treat each direction separately. You could actually have a net force in the x and not in the y, or you could have a net force in the y, not in the x, or you could have a net force in both x and y. And finally, we're going to be adding forces that work in the same direction. We're going to be subtracting forces that work in opposite direction, like vectors. So net forces, which are the amount of unbalanced experienced by an object. This net force will overcome the inertia and change the motion of the object. Newton's first law says the object wants to resist the change of motion, but it also states now the second law that if you have an unbalance, it will always overcome the inertia and change its motion. The amount the object will change its motion depends on either how much net force there is or how much inertia it has. And there's a little summary right there. So to summarize what I just said in the summary, that's kind of awkward. A net force acting on a mass causes it to accelerate in the direction of net force. So the larger the unbalance, the larger the acceleration. But the larger the mass, the more net force you need to make it accelerate the same. Pushing to make let's say you want to push a small person. Shoving them over, a small force can make them accelerate a lot. But if you're looking at a big person, to have the same change in motion, you have to put a lot more force in there. So here's Newton's second law. It is not a written law with words usually. It is represented mathematically. Its net force is mass times acceleration. Where the net force is always a vector. It has an amount and a direction. The amount is called the magnitude. And it also has a unit. All forces have this unit. Since mass is in kilograms and acceleration is meters per second squared, net force is kilogram meters all over second squared, which we usually call a Newton, represented by N. So if there's no change in motion occurring in the direction, the net force for that direction is 0. That does not mean that there are no forces in that direction. Right now, hopefully you're sitting or standing or something. You're not moving up or down. That means there's no change of motion up or down, which means there's no net force up or down. But there are forces that worked. There's your weight, that's the pull down on you from the earth, and then there is the upward pull of your chair or the ground. And those two forces are balanced. Big point. If an object's moving along a surface, the acceleration perpendicular to the surface is 0. Therefore, the net force perpendicular to the surface is 0. If you're sliding on the ground, you're not moving up or down, which means the net force up and down is 0, which means the forces up and the forces down are balanced. Now let's apply to math. Since all forces are going to be in newtons, we can come up with an equation for force we know. 1 kilogram on the moon has a different weight than 1 kilogram on Earth, because on the moon, the pull of the moon on the kilogram is different than the Earth's pull on the kilogram. The mass doesn't change, but the weight does. Let's use Newton's second law for the weight of something on Earth. And we're going to find the equation. Weight is mass times gravity. Since weight is m times a is gravity, where g is the gravitational constant of the distance from the planet. So as you get farther and farther from Earth, the gravitational acceleration is no longer 9.8 or 10 or whatever. It is going to be less and less and less. So we have one equation so far with the net force equation. That's two equations overall. Here's our example. Write it down for me, please. Two ropes pull on a 50 kilogram car. One has a tensional force of 300 newtons to the right. The other has a tensional force of 200 newtons to the left. Ignoring friction, find the acceleration of the cart as it moves on the table. Whew. Step 1, always draw a free body diagram after you've underlined the key phrases in the example. So looking at the example, I underline 50 kilogram car, that's my inertia. I have a tensional force of 300 to the right, that's at one force. I have another 200 newtons to the left, I underline that as well. Ignoring friction, underline that. The acceleration, underline as it moves on the table, underlined. Here's my free body diagram. 50 kilogram car, and I have 4 forces. The weight, force of the earth on the car, pulling it down. The normal force, force of the ground on the car, pulling it up. Force 2, the force of the rope on the car left, 200 newtons. Force 1, the force of the rope on the car right, 300 newtons. Okay. The second thing I'm going to look at here, after drawing the free body diagram, let's try that again. After I draw my free body diagram, I know since it's moving only on a table, it's moving only on x, horizontal motion. So y is in equilibrium. So to find the acceleration, I don't care about y because it's accelerating in the horizontal direction. So ignore the y forces unless we need them to calculate something in the x, like we did with projectiles and we'll do later on. With that, my free body diagram is really looking like this. 300 force to the right, 200 force to the left. The y forces are imbalanced. They do not affect the acceleration. So in the x direction, the force right is greater than the force left. So the car is going to accelerate to the right. Positive, negative, relative. Right is not always positive. It's just we're going to look at the direction of acceleration. Whatever direction is accelerating, let's call that positive. The net force is the amount of imbalance. The forces are opposite, so we subtract. 300 newtons minus 200 newtons will equal 100 newtons to the right. You could also use the phrase positive 100 newtons if you define positive as the direction of acceleration. Our goal is acceleration, and we know the amount of imbalance. Net force is mass times acceleration. So I'm going to plug in 100 to the right as my net force equals ma, and the mass is 50 kilograms. So I'm going to solve for the acceleration and find it to be 2 meters per second squared to the right. So 2 questions. Question number 1. Actually, I think there's only 1 question. Question number 1. Can you determine if the car was moving right at the time? There are 2 questions. No, you can't. The car could be moving left, but this force may be slowing it down. And acceleration does not guarantee a direction of motion. All you know is that the right force is more than the left, which means that it's accelerating to the right. It could have started to be moving left, and now you're simply trying to jerk it to a stop. Or it could be moving right, and you're trying to speed it up, but you can't tell from the situation. Question 2. Can you determine the normal force in the car? And the answer is, yeah. Again, the motion in the x means the y forces are in balance. So in this case, not always true, the normal force is equal to the weight, since they're the only 2 y forces and they are in equilibrium in the y. So the weight, mass times gravity, I got 500 newtons down. The normal force is 500 newtons up, balanced. And now finally for the third law, sometimes called the law of action or reaction. The force on object A from object B is equal in magnitude in opposite direction from the force of object B on object A. They're called companion forces or action-reaction forces. If you push me, I'll have an equal and opposite reaction on your hand backwards. It's really easy to screw up. So for example, in this example we had a little while ago, the weight is the earth pulling down on the car, the normal force is pushing up. What is the companion force and normal force here? Well, most people would say it's the weight because it's 500 newtons and it's down. But I'm going to say no. Kind of like reverse the wording on here. The opposite of normal force is not the weight of the car. It's the force of the car acting on the ground. I'm going to say that again. The opposite of the ground on the car is the car on the ground, which is not necessarily the weight of the car being pulled down by the earth. Now, a really awesome and weird thing here. Let's say you jump up in the air. What's going to pull you back down to the ground? Well, we're now officially going to say that your weight, that downward force of the earth on you, is going to pull you back down. So what's the opposite force or the reaction force there? It is going to be you pulling the earth. So when you're jumping up, even though you're moving up at first, the earth is going to pull you back towards it. And as you come back down there, you're getting pulled by the earth back towards it. At the same time, you are also pulling the Earth up towards you. Does the Earth actually move? Absolutely. Because from the Earth's point of view, it now experiences an unbalanced force, a pull towards you. But it won't move the same amount you do because its inertia is so much more, it will barely have an acceleration from the same force. Whereas from the same force, you, which are gigantically lighter, will have a gigantic acceleration compared to the Earth. Your acceleration will be -10. Their acceleration will be like around 24 decimal points before there's a 1, but it's still there. And with that, wonderful students, take care.